Hi, everyone, and welcome to the second session of this week, week 2, basically. Today is Thursday. We're regularly meeting now at 2:10 p.m. And you should be receiving a reminder about 10-15 minutes before class starts about the class. So make sure you watch for messages from me. This is a continuation, basically, of the topic we started on Tuesday. Today, we're going to focus on the moon, the motion of the moon basically around the Earth. And of course, the Earth is moving around the sun, and that gives us some sort of a correlation between these two motions, namely the motion of the Earth around the sun and the motion of the moon around the Earth. So that's basically what we're going to be focusing on. Obviously, we are, from our vantage point, we have an apparent motion of the moon. Let me go back. Apparent motion of the sun around the Earth, that's for sure. Okay. Then there is a kind of two motions for the moon that we have to understand. First of all, a real motion of the moon around the Earth, and that takes about a lunar month to go once around the Earth. Okay. But there is also a daily motion of the moon around the Earth, and that is the moon will rise at a certain point and sets in this another point, and so on and so forth. But that is actually due to the rotation of the Earth. You have to make sure that that distinction is clear. And that too is true also for the sun. We have a yearly motion around the sun, that is the year, that is the calendar, and so on and so forth, the solar year. And then also we have a daily motion of the sun around the Earth, or at least an apparent motion of the Earth, the sun around the Earth. And that is due also to the same thing, which is the rotation of the Earth around its own axis. So that is the two motions for the moon that we're going to be focusing on. So the first one is a motion around the Earth that takes a lunar month. And then a motion of the moon around the Earth also, which is about a day, which is about 24 hours. And that is due actually to the rotation of the Earth. So this is basically what Unit 8 is focused on. Focuses also on the moon phases, because the moon, as the Earth rotates, as it goes around the Earth, I should say, it goes through several phases. So we're going to talk about those phases of the moon, and they last from the beginning of the lunar month until basically the end of it, and they repeat on a cyclic phenomenon. So this is the thing that we have to focus on. So let me share with you the notes, which you should find actually on your on Canvas. So these are the PowerPoints. So the moon fascinated humans from basically the dawn of time, from the time that we can record, when the time is recorded. And because, first of all, it's a big sight in the night sky. It occupies a huge part of the night sky. And second, it's when it's full moon, at least, it's big, and it's also so much light is coming from it that people basically has a lot of influence over the culture in general, literature, poetry, religion, and everything else. So everything is a lot of things related to it. One of the words that probably you hear a lot in our culture is the word lunatic. It seems like at least some studies think that there is some sort of correlation between when the moon is full and when behavior of people is not really up to par or up to standard. So that behavior is basically crazy behavior, and that behavior is related to that word lunatic. So it seems like there's some sort of studies that seem to confirm and deny this relationship. And maybe it has to do with the fact that there is more light during that time, so people probably don't have as much sleep, so they behave more normally. So again, the moon has played a major role in our culture, and whether in poetry, whether in literature, whether in science, whether in religion, whether in all kinds of fields. So that's basically what the whole point of this thing is. Not only the moon basically moves around the sky, as I was saying, it also changes shape. Sometimes there is barely part of it seen in a crescent format, and sometimes the crescent is pointing toward the west, and sometimes the crescent is actually pointing toward the east. So That is one way. There is some other times actually there is a bulge in it too, and the bulge could be pointing toward the east or toward the west, depending on the time of the year too. And at times it's basically half of it is lit and half of it is dark. And at some other points in the month, it's completely lit. Okay, so we gave them names. These phases of the moon, we gave them actually different names depending on how they appear. It seems like when in the beginning of the lunar month, there is that crescent pointing toward the west. Remember, the sun sets in the west, so immediately after the sun sets, we see a crescent, a side that is pointing toward the sun. As days move along, that crescent starts to increase in size, and as it is increasing, we gave it a name, a waxing crescent. So it's an increase, it's wax, it's basically it's increasing in size. About a week later, it's going to also move. I mean, it's going to set later on in the day too. I mean, in the night, I should say. Okay, so it rises, the sun sets, it rises, and in the beginning it stays only for probably less than an hour, and then the next day is going to be almost 2 hours, and the next day more and more, until basically it stays half of the night, basically, when the it sets from the middle, and then in the dawn when it's going to leave. So at that time we have a quarter moon, because think of the moon is divided into 4 cycles, because this is how the idea is. The lunar month is 29.5 days, just short of 30 days. This cycle repeats every 7 days, every week, 4 weeks, basically, every once a week in 4 weeks. So when it's the first quarter of that time, about a week, you have the moon that is half lit and half dark. So we call that the quarter moon. Then it starts to grow more than the quarter. For the next 7 days after that, it's growing in size. So in this case, it becomes what is known as a gibbous. And the gibbous in here means that it's bulging, that's all. Okay, so it's a gibbous, and that gibbous is increasing actually. The bulge is increasing in size. So it was quarter, and now it's increasing in size. Okay, so we call it still a waxing, but gibbous this time around. It's not crescent anymore. Until midway in the 29.5 cycle, which is about 2 weeks, then at that point the moon will be fully lit, and we call that a full moon. Okay. Then after that, it starts to shrink from the western side, and the eastern side stays completely as is. And as it's shrinking, the bulge now is pointing in the other direction, but it's decreasing with time. It's less and less. So it's a waning, meaning that it's decreasing in value, gibbous, which is the same thing as bulging. Okay, so it's waning, meaning it's shrinking in size. After 3 weeks, basically from the start of the whole process, the moon again will be half lit, except in the opposite direction. Remember, in the beginning it was like this. Then now it's actually like this. So in a sense, now what you have a quarter, but it's not the first quarter, it's the third quarter of the whole cycle of 4 weeks. So basically the cycle of 4 weeks, now we're in the third week. So that's 3/4 of the whole way. So we call it 3/4 moon, okay? Or the third quarter. The moon is in the third quarter. Now, for the next week or so, the moon starts to shrink. Now it's no longer gibbous, it's no longer bulging. Now it's more of a crescent, but that crescent is decreasing, it's waning. So we call it a waning crescent, until it disappears completely, and it appears from the other side again, and the whole cycle repeats. Okay, so this is basically the different phases of the moon. We're going to have an activity which I'm going to open up in about 2 weeks or 3 weeks from today, depending. where you're actually going to monitor this activity of the moon for a full 4-week cycle. You're going to go specific nights outside, and you're going to document, first of all, the time when you went, and the date, of course, and the shape of the moon. Mind you that it's not always at night. It might be early in the morning. So if you miss it and you don't find it anywhere at night, hey, it's probably in the morning. So you have to wake up a little early, 5 a.m., 6 a.m., 7 a.m., sometimes even 9 a.m. and it's still 10 a.m. and it's still in the nights. I mean, in the sky. Even when the sun is up, you can still see the moon. So you're going to monitor the moon. You're going to tell me its approximate location and its phase. Okay, that is the activity. That is why this whole unit is actually important. It's because it ties in explicitly to that activity, and that is graded separately. So that's a project that you're going to submit. Obviously, you will be given guidelines. You'll be given instructions into what you should look for and what you should do, and so on and so forth. But this is the overall idea. Makes sense so far? Yes. Okay. Very good. Thank you, Samantha and Gabriel. Okay, very good. So the point being in here is that as long as we have these big ideas, then hopefully we can have more details down the road so that we understand what's going on. Okay, then the other thing also, I already described it, the position in the sky versus the face. It really is critical to understand which side is lit, depending whether it's a gibbous or a quarter moon, basically half lit, or a crescent. Just by looking at which side is lit and which side is not, in the beginning of the month, the moon is actually chasing the sun. And toward the end of the month, the sun is actually chasing the moon. So that's basically what's going on, at least for your own, that's how you see it. So when the sun is coming from this side, it's this side that is lit. When the moon is chasing, it's this side of the moon that is lit. So the east or the west, depending on if you are in the beginning of the lunar month or the end of the lunar month. And then we have another issue that we're going to discuss, and that is the lunar eclipses and the solar eclipses. Basically, in a nutshell, and this is part of the activity why I have the book in here for you guys, and I hope that you brought it with you and you have at least access to it, because we're going to do some problems from there to understand what's going on, is that at times, the moon covers the sun completely during daytime. So the day becomes night. This is a rare event. The solar eclipse is not a common event, so it's an extremely rare event. And then at other times, actually, the Earth intervenes between the sun and the moon loses most of its whitish color, basically, and becomes more of a reddish color. Okay, so it loses a lot of its brightness. And then it resumes. After a few hours, it resumes back to its normal color. This is the lunar eclipse. And this too happens rarely, but more frequently than the solar eclipse. Okay. And the question that I think is part of the discussion is, why wouldn't we see a lunar eclipse every month and a solar eclipse every month? Because as the sun is moving around the Earth on a daily event, which is due to the Earth moving around its own axis, the moon is actually moving around the Earth, physically speaking. So the moon can should be at sometimes between the Earth and the moon. In this case, it should cover the sun. We will have a solar eclipse. And at times, the Earth actually, because it moves to the other side, the sun is still extremely slow motion because the Earth has to take a whole year to go around it. So the sun barely moves during that time. So in at least a month. So the moon now should be behind the Earth, and it should be completely covered by the Earth. So we should have a lunar eclipse. Yet, as I said before, these two events are rare. They don't occur on a regular basis. The last big event that happened, I believe, was in 2017 for the solar eclipse. Any one of you remember that? happened big time in North America overall, but mainly in the Midwest. And I happened to be in Missouri at that time, so it really went completely dark for a few minutes. Anyone remember that event, 2017 solar eclipse? No? Okay, very good. Okay, very good. At least I have a couple of people who enjoyed it. So anyway, the point being in here is this is a rare event, and we really need to understand why that is. I mean, in a nutshell, the answer to that question is not a mystery, and it has to do with the path of the moon around the Earth and the path of the Earth around the sun. And they're not actually on the same plane. Those two paths are not coplanar. In other words, they make an angle with respect to one another. So the moon comes in and out of the path of the Earth around the sun. So unless it lines up perfectly, when it's on the same plane, because it crosses it, once it crosses it, then you will have a solar eclipse and a lunar eclipse. If it doesn't, then it's not going to happen. And then the trick behind it also, if you have a solar eclipse or a lunar eclipse in the same month, you will have the opposite. Okay, because of that crossing. Unless it crosses it at a bigger angle to begin with, more than 1 degree, and it keeps deviating, then in this case, you're going to miss it, at least for most of the planet. Maybe you're going to have partial eclipse somewhere else. Okay. Obviously, we're going to talk more about the eclipses to understand that there is a full eclipse, there is a partial eclipse, and there is this distinctions. Okay, so these are the topics of this unit. I think we went through a lot of them, but let's get into the details. Okay, so again, I said before, the moon takes about 29.5 days to go around the Earth. That's not true. It's 27.3 days, or 27 and fraction of a day to move around the Earth. But because we're referring to it in terms of how it's born for us, a new moon is born basically when it's on the same side of the sun. So at that time, we don't see it. That is a new moon. Then it's going to keep on basically moving away because it moves a lot faster. It's actually the fastest object moving around the Earth on a daily basis, and we can track that down with Stellarium. Then it's going to grow to go through all of the phases I described before until it's full moon when it's on the other side of the sun. So the sun lights it completely and it reflects back to us and we see the whole thing. Okay, so that is the full moon. And then it's going to start to go around until it becomes again lined up with the sun so that we don't see it again. And at that point, it's born again for the next month. So you'll have a new moon and go through the entire cycle until it completely ends. And then you're going to start again with the new moon. So that cycle is 29.5 days. Maybe basically from new moon to new moon is 29.5 days. And the actual rotation is a little less. You ask, where is the difference is coming from? From the same reason that the day is not exactly 24 hours, but 23 hours and 56 minutes. The sidereal lunar month is less than the lunar month as we know it on a day-to-day basis. In other words, if the moon were lined up to another star, of course, we're going to have, and we're going to talk about the sidereal lunar month. But the point being in here at this point is the moon goes through all of these four phases that I mentioned before, all of these phases that I mentioned before. Since 29.5 is divided by 4 is about 7 point something. Let me do the math in here to give you an exact number. 29.5, and you should be able to get your calculator. It doesn't have to be a fancy calculator, any calculator will do. And I'm not getting any answer in here. Divided by 4.2. 7.4, basically 7.375 to be more specific. So in a little less than 7.5 days, each one of this will go through it from the beginning, from the new moon, when you cannot see it at night, because at that time it's basically hidden. It's during the daytime when it's actually born. Then it starts to show that little crescent I was saying. Note where the crescent is pointing to. It's very critical to understand where it's pointing to, because the sun is assumed to be setting in the west. It's not because it's assuming, it is going to set in the west. So it's setting in the west. Then in this case, the moon has the light that is lit is the one that is pointing to the west, because that's where the sun is coming. That's where the rays of the sun are coming. Okay, so the sun is setting and it's following it, because remember, they were just lined up. Now it's racing away from it, so it's the side that is that was facing it that is lit, and it's going to grow and grow and grow. And this is a waxing crescent. It's an increasing. On exactly around 7.4 days, which is a week later, it's going to be the first quarter moon. Okay, that would last for about a day, and then after that, that will start to increase, and that is going to have a bulging, and that bulging is going to increase and increase and increase, and we call that one, because it's increasing, a waxing gibbous, until another 7.4 days, which puts us around 15 days. Then we have a full moon. The entire moon is lit. But then, when it's full moon, it's actually going, when the sun sets, the moon sets in the west again, the moon will rise from the east and stays the entire night in the sky. When it's full moon, it's going to light the entire night from sunset until sun up. The next day, the moon is basically going to go to set at that time. Okay, so it's a full moon. So because it's on the opposite side of the earth versus the moon, versus the sun. Okay, and there is no full moon because, as I was saying, think of the three objects as lined up, not exactly on the same line, but one of them on the other side. So if there is light coming from here, it's going to shine on the moon, and we're looking at the moon and we see it lit. So it's not exactly lined up. There is a differential, and that differential with the ray is coming, and we're looking at it as a full moon. Okay, but then the sun will start rising again in the east, and the moon starts lagging now behind it, because the sun is catching up with it. So it's catching up with it now. It's lighting the eastern side of it, but the western side of it now is going to go around the earth, so it's going to be hidden from us. So at that point, the bulging that starts to decrease in shape now. It's less and less and less. And that is what is a waning gibbous is. Shrinking, bulging, if you want to call it that way. In about 3 weeks from when the whole thing started, you have another quarter now. You have half moon basically lit. And that is the third quarter. The reason why it's called the third quarter, because this is the first quarter, this is the second quarter, and this is the third quarter, and this is the beginning of the fourth quarter, if you wish. So this is the third quarter. This ends the third quarter. Okay. Now, this process will continue, because now the moon is lining itself between the earth and the sun. So the side that is lit is on the other side. We don't see it. We see just the dark side at that point, or an ever increasing dark side from it, an ever decreasing shiny side from it. So at that point, the moon is a crescent again, but in the opposite direction, pointing toward the east now. So if you see a moon that is crescent with the lit side pointing toward the east, then understand you are at the end of the lunar month, not in the beginning. The beginning will be lit on the western side. So at that point, it's going to start decreasing. It's a crescent still, but it's a waning crescent. Okay, this one is a waning gibbous. This one is a waning crescent, until at the end, the last basically sliver of light in the crescent will disappear, which will put us back in the new moon, and the whole thing repeats. So these are the phases of the moon. By basically, everybody agreed that this is the beginning of the lunar month. You might be rightfully asked, especially if you have a math background, why can't any point be the beginning of the lunar month? And you're absolutely right. But by convention, this is the beginning of the lunar month, okay? For math-minded people, because this is a cyclic event, so any point can be the start. I mean, what I mean by it is, don't look at the circle as the center of the circle, because the center of the circle is something. What I'm talking about is the perimeter or the circumference of the circle. Which point is preferred in the circumference? It doesn't matter. They're all the same. Okay. Here's the point I was making earlier about the difference between the actual rotation of the moon around the Earth and its own, basically on how we keep time, how we keep the lunar month intact. Okay. We say a new moon happens when it sits between us and the sun. Remember, it doesn't have to create a solar eclipse, because that will have a solar eclipse if it covers the entire sun. Okay. And you're asking, how is it going to cover the entire sun when the sun is huge and the moon is tiny? And that's a legitimate question. And actually, it's one of the questions we're going to answer later on in one of the problems. And the answer in a nutshell is the moon is closer to us. If you take a nickel and put it in front of your eye, it can cover the entire room. Although the nickel is a lot less than the room. So that's exactly the same idea in here, okay? So, so this is the new moon. In other words, the part, and it's doesn't have to be lined up, it could be just off. The moon that is lit on the other side, and we don't see anything at this point. So this is the new moon, okay? So the moon was born in this case. And then the moon goes through the entire 360 degrees around the Earth if we refer to it in terms of faraway stars. Okay. Its position versus the constellations, for example, a given constellation, a given star in a constellation, then we know this is what it is today. Okay. Then a month later, when it goes through the entire cycle, goes around the Earth, the time that has lapsed is 27.3 days on Earth. In other words, the Earth would have done 27 days and a third of a day. Okay, 27 days and 8 hours, to be more specific. Okay, that's a third of a day, because 24 hours divided by 3 is 8 hours. So that's what the third of the day means. Okay, then it would have gone through the entire cycle. But it's not moon anymore. I mean, it's not new moon anymore. It's still a crescent. And in this case, it's a waning crescent because the sun is still partially showing part of it. So for it to be a new moon again, the Earth has to rotate an extra 2 days and some change, 2.2 days to be more specific, to bring it in the alignment with the sun again, so that the new moon is born. So for us on Earth, when we count the days, the lunar month, we start from when it's a new moon, and we go, and then it's a new moon again. That is 29.5 days. The actual rotation of the moon, the sidereal lunar month, is actually only 27.3 days. Okay, so this is the distinction in here. It has to do with the same reason as we discussed last time about the day being 24 hours by convention, and then in doing so, the Earth has to rotate a little less in comparison to the rest of the actual rotation is a little less, and it has to rotate that extra 4 minutes to align the sun on the noon, on the local meridian. The sun, when we started counting, we said, okay, noon is the starting point. Wait the next time when there is noon, basically the next day when it's noon, when it passes through our local meridian, at that point, it's noon again. We decided by convention that's 24 hours. Obviously, the Earth would have made a full rotation and then some change to align the sun back to the same place. Okay, why? Because the Earth is moving around the sun. It's moving around the sun, so it has to make that extra turn to make up for that motion, so that it's aligned again with the sun. The same thing is true in this case. And this is also due to the same thing, which is the motion of the Earth around the sun. In other words, if the Earth is nailed, you take a nail and you nail it, and the sun also is nailed, because if you nail the Earth, the sun is actually moving in the galaxy. So if you nail these two, okay, then the moon will, the lunar month will be just 27.3 days. End of the day, end of the discussion. Okay. But it's not so, because the Earth is actually moving. Nothing is nailed, everything is moving. So the Earth has to make this extra 2 days to bring the moon up to par, so that the light is completely gone, and at that point we have a new moon again. Makes sense? Yes? Very good. Thank you. So again, I was talking about the different cycles in which part is lit. Always look for the sun. If you see the moon lit toward the lit part of the moon is pointing toward the west. In this case, the moon is following the sun. And in this case, we are in the beginning of the lunar month. The sun just set. The moon, the part of it that is lit in this case, is pointing to where the sun is setting, which is the west. Okay. So in this case, we have an increasing crescent. So this is actually a waxing crescent until after 8 days, when the sun sets, the moon actually is midway in the sky. And it's going to stay there until the dawn. Basically, it's going to set early in the morning around this side, and this is where it's going to rise. So it's going to rise in the middle of the sky. Later in the month, around 11 days just before the full moon, in that case, the sun sets and the moon appears actually a little bit to the east in this case. It rises in this position. It's going to continue following in this direction until it sets in the morning again. Now, on a full moon, the 15th day, when the sun sets, the moon rises in the east. The sun sets in the west, the moon rises in the east. And it's going to be completely lit, and it's going to light the entire night for us. And it's going to stay the entire night in the sky. When the sun rises in the east, then the moon sets in the west. Now, this is only true when it's a full moon. The opposite is true from day 15 now. When the sun rises, or just a following of this, when the sun rises, the moon is setting, actually, being a full moon. When the sun rises, a little later, the moon is still in the sky in here, and the sun is following it. And again, as the sun is rising, it's shining the eastern part of the moon now. Okay, so around the third quarter, when the moon is in the third quarter, at that point, when the sun rises, the moon is still in the middle of the sky. So you can actually see it. Okay, early in the morning, you will see the moon in there. Further in the week, yes, before the end of the lunar month, as the sun rises, the moon is actually in the sky, in the eastern skies. Okay, and it's still actually, in this case, it's a crescent, but it's a waning crescent. And then toward the end of the month, just before the end of the lunar month, as the sun rises, the moon is just ahead of it. And it's actually a crescent, smaller and smaller crescent. And at some point, it's going to disappear. So when the sun rises, there is no moon. When it sets, basically, there is no moon. And that is the new moon. That is actually when we talk about the new moon, when it's born. Okay. This is, again, in the beginning of the lunar months. As the sun is setting, the moon starts to appear in the sky. Okay. This is day 4, day 8. And again, this is toward the end of the lunar month. As the sun is rising, the moon is at the sky. Actually, I was talking about it in here too. And this is midnight and how it looks like on a different times of the lunar month. And the 8th day, which is in here, when it's midnight, the moon, remember, it rises in the middle of the sky. When it's midnight, it's setting. When it's a full moon, again, when the sun sets, the moon rises, and it's going to stay the entire night. So midnight is going to be in the middle of the sky. And the same thing is true toward the end. So in this case, midnight is the moon just rising in this case, and it's going to be caught by the sun when it's rising right in the middle of the sky. So this is the different, basically, versions of this. And again, it's illustrated also by this diagram into how everything looks like. So again, this graphic will explain a little bit more about these phases. This is the new moon. In this case, day 0, basically. This is the starting point. The moon is in the same direction as the sun. When I say the same direction, it's not the same plane. You have to make that distinction. I know I mentioned several times now. It means that's overall direction. Okay. Waxing crescent is the first week, basically. So near the sun in the early evening sky. First quarter, 90 degrees from it. So they make a 90 degree at that point. Waxing gibbous is far from the sun in evening sky until after midnight. Full, it's around 15 days, basically, opposite to the sun, rising at sunset and up all night. Waning gibbous, third quarter. So all of these things explains everything I was talking about earlier. Okay. Now, in terms of the solar eclipse, I mentioned the path of the sun and the path of the moon. Do we have another paper in here? I don't know what this cover is for. I'm going to use it anyway. So this is, think of this as the path of the sun, and this is the path of the moon. So they are not exactly lined up to be covering one another, but there is an angle between them, and that angle is about 5 degrees. So the moon could be 5 degrees above the ecliptic, 5 degrees below the ecliptic at any time of its path. Because of that, when it's a full moon, most of the time, there is no Can you guys hear me? For some reason, my camera is having a problem.
Yeah, we can hear you.
Okay, very good. Sorry about that. I don't know, the whole thing stopped working right now. So now my camera is not working, which is a problem trying to explain these points in here. So let me share with you the PowerPoint, just in case. And I have the camera on. Why is it not working? Oh, no, I want this camera. Okay, very good. Now the camera is back. Very good. Sorry about that. Okay. So anyway, let me share still the PowerPoint. So again, my point in here is that these two planes are not coplanar. They're not on the same side. That's why we don't see lunar eclipses and solar eclipses all the time. There is an inclination of 5 degrees. So the moon is moving in this path. Okay. So it's sometimes in the lunar month above 5 degrees, and sometimes it's below 5 degrees. Unless it is caught right within 1 degree above or below the Earth ecliptic, that is, the ecliptic plane, we will not see lunar eclipse or solar eclipse. That is the bottom line. So if it's within a degree, then in that case, either a plus a degree or a minus a degree, then in that case, we will see lunar eclipses or solar eclipses, okay? So that is basically in a nutshell what this whole thing is, okay? So again, you will have either a full lunar eclipse or a partial lunar eclipse, meaning that part of the moon goes under the shadow of the Earth for a partial eclipse. Or in this case, it's actually called a partial eclipse, but then it's also penumbra, which is not the entire shadow of the Earth, but part of the shadow. So in that case, it's even different kind of eclipse. That's most of the eclipses. That's why we really don't see them, because the dimming is so little that it's not even recorded, okay? When it goes through the penumbra. Again, there is the actual shadow, which is, this is called the umbra, and then there is the penumbra. So it goes through these two paths, which are the rays crossing in this case. Then it's going to lose some of its light, but not as much as you might suspect. So that's why it's not lunar. Same thing for the sun. You could have a partial eclipse or a full eclipse, depending on where you are on Earth, okay? Depending on where you are on Earth. Again, remember that 1 degree up and down, that also determines the intensity of the eclipse. So those are basically the process through which you can have an eclipse. Obviously, in this case, we're talking about a solar eclipse, because the moon is covering the sun. Okay, but it's covering it only in that region of the Earth where it's going to have a full solar eclipse. Regions above and below and around it are going to have partial solar eclipse. Regions far away, they will not even see that. Okay, they will not even see that eclipse. And this is how the projection of the shadow of the moon would look like on a specific point in here on Earth. This chart is important. This is the one that we're going to base our problem that we're going to discuss later on, because it can give us some sort of an indication when the last eclipses happen. Okay, this is the one I was talking about in 2017. This is the one that went through the entire Midwest, August 21st, 2017. That was when the school started. Immediately after that, the next week we had a major solar eclipse. And as I said before, I happened to be in Missouri at that time, and it was really something that was very nice to have. This is a solar eclipse that happened last time on Earth. Okay, the United States will experience something along that lines, but it's going to pass through Texas and also some of the other the Midwest and also some of the eastern states, but not through the West. That is going to be in April 8th, 2024, okay, which is in about a year and a half from today. So that's something nice to look forward to. Other parts of the world that is going, at least that are accessible. I don't go to South America, but this one happened in 2020. This one is actually happened in 2019. This is going to happen in Alaska in 2033. 2015 is also somewhere in the ocean in here. And there is this one that I'm personally looking forward to, because that is going to be something that I could do. And that is in most of Spain and some islands in the Mediterranean. So they are going to experience actually a full lunar eclipse. Maybe even southern France and maybe even northern Portugal will have that experience. So I happen to be in Barcelona at that time. It's a beautiful thing to see. That is actually going to be in August 12th, 2026. A year later, August 2nd, 2027, it's going to be mainly in North Africa. Okay, that is something that also I probably could do, and that is something that is nice to see too. Okay, the problem that we have from Unit 8 on page, was it 68 I said last time? I think I did say 68. Yeah, 68. Deals with this chart in here in making a prediction in when the next solar eclipse is going to happen, and you will see that it matches exactly, the theory matches exactly the model matches exactly the predicted value, and it's going to happen sometime in 2045 here in North America. It's all based on this one, based on the one that is going to hit North Africa on August 2nd, 2027. Okay. So again, this is how the paths line up, and when it's a lunar eclipse, which is a more frequent, the moon basically gets this reddish color. And you're asking, why do we have a reddish color? It's because the rays actually that block the moon from the rays, the Earth blocks the moon actually in this case, and it's supposed to be completely dark, but because the Earth has an atmosphere, it deflects the rays. Just what happens when you go outside, for example, during sunset or sunrise, actually the night looks different, looks kind of reddish color. And that is because how rays of the sun are going to be scattered. This is known as, this is a scattering of rays. The reason why the sky looks blue is because the rays, and it's not because of the ocean is blue. The ocean is blue because the sky is blue, appears blue to us. It's because the rays as they're coming from the sun to us, the radiation from the sun, it has the entire spectrum in it, from red light all the way to ultraviolet light, to violet light. It has actually outside of the infrared also, and also the ultraviolet, but the visible, the things we can see are from the violet all the way to the red. The red is long wavelength. The violet is very short wavelength. Okay, the blue mainly in this case, because blue is more frequent than the violet, it's more intense. So what happened in this case is the long wavelength gets scattered in all directions, and the blue in this case goes through. So the sky appears bluish to us. Okay, so that's why the sky is blue. It's because of the scattering of the rays. In the evening, though, what happened in this case is the sun actually has already set on the other side, and it's reflected and it's coming to us in the one that is scattered, which is the red in this case. Of course, the blue in this case is not going because it's looking somewhere else, pointing somewhere else, pointing to the people who are actually on the other side of the Earth looking at the sun. Now, this is the same thing true also for the case of the moon when it's a lunar eclipse. The rays actually go through the Earth, and the long wavelengths are scattered. The blue wavelengths are actually going to go straight through, and that is going to continue through, and it's going to miss the moon, but because the long wavelength, the red light is going to be scattered the most, and that is going to hit the moon, and that's why the moon appears red. It's the same reason for the sunset and the sunrise, for why the night looks like that way. Anyway, so this is discussion of the lunar eclipse, and basically the two types actually, and how long the lunar eclipse can last. And this is the 5-degree I was telling you about. So the path of the sun, the path of the moon, I should say, it's on this line, the orbit of the sun, and the path of the Earth, which is the apparent path of the sun, is the ecliptic, is this one. They make 5-degree angle. So there is, on a monthly basis, this phenomenon of the shadows, but we miss it all the time. For example, when it's a new moon, we don't see a lunar eclipse. Why? Because the shadow of the moon is missing the Earth entirely. It's below. That's the moon's umbra. It's missing the Earth completely. So there is no portion of the Earth that is going to see the solar eclipse. If it is in this side, even if it's closer in here, you're not going to have it either. So it has to be within 1 degree to start hitting the Earth. The same thing in here for the moon. When it's full moon, it's not covered by the Earth because the shadow of the Earth will miss it entirely. This is the Earth's umbra. So it's not going to cover the moon at all. So in this case, you will not have a lunar eclipse either when it's full moon. Unless the moon is somewhere in this area in here. Of course, it's moving around the Earth. It's not hitting the Earth. So this is just a cut across the path. So when you take a path that looks like this, and you look at it at an angle, it looks a line. So that's exactly what you're looking at. You're looking at it from sideways. So when the moon is going around the Earth, but it's close in here, yes, in this case, you're going to have a lunar eclipse, as long as it's within this 1 degree. Right now, it's far away from it, okay? So that's basically how this, granted that this is kind of misleading. You have to be careful in here. It might be tempted that this is a 5 degree, whether you look at it here or here or here, but it's actually moving around as coming from 5 degrees down to -5 degrees. So at some point, it's going to be within 1 degree. So that is how you can have a lunar eclipse. and solar eclipse. It's because of this one. Okay, so in a sense, this is we answered the discussion item. Okay, so this is the answer to the discussion item this week. Okay. Again, the only reason why you will have a solar eclipse, like in this situation, or a lunar eclipse, a solar eclipse in here, or a solar eclipse in there, is as long as you have this within 1 degree, or actually a lunar eclipse when you have it on the other side, when the moon on this side or the moon on the other side. Okay. Again, that's when you catch it. It's when these two paths cross. Okay. I think we discussed this unit hopefully in greater detail, and I'm hoping that you will not have any problems doing these problems, discussions and all of the other things. Any questions before I delve into the problem I promised to do? Okay, so let me share with you the, let me open OneNote first. Where is my keyboard? Okay, so in here, let me at least, let me share with you first the screen. Share. Okay. Drawing. Let me change the color of the pen. Okay. So in this case, as I said before last time, we're going to discuss actually problem 15. Is this too thick? I think it is. And 16 from page 68. Okay. And if we have time, we're going to do from unit 9 also. Okay. I think some of these things are assigned later on as homework problems, so you should be able to do them if you have once they're assigned. Anyway, problem 15. Show. So this is 15, okay? Show that the ratio of the moon's diameter to the sun's diameter, this ratio, is similar to the sun's distance to the moon's distance. Okay. Sizes needed to solve this are in appendix table 1 and 7. So you really have to have access to the book and also online or actually in printed version to do this. So we have to get into appendix, excuse me, 1 and 7. Tables 1 and 7. What are they? Okay. If you look at the appendix, table 1, and that should be on page, actually there is no page number, I'm sorry. It's the appendix starts on after page 700, 701, then maybe 703. There is no page number on this appendix, okay? Let me show you what I'm looking at in here. So this is basically how it looks like on this book. So for you, if you have access to the book online, you're going to go and find where the appendix is. And it says appendix table 1. So we need appendix table 1, excuse me, and we need to pull from it the information related to the moon and the information related to the sun. So from this one in here, it says, let me make sure I have the, yeah, tables 1 and 7. So table 1 says the velocity, gravitational constant, Planck's constant, mass of hydrogen, mass of electrons, Stefan's Bill's law, astronomical unit, light year, parsec, year, and mass of the sun, radius of the sun. Remember, we need the radius of the diameter of the sun, and the radius is diameter is just twice the radius. So they gave us the radius of the sun, and radius of the sun, according to this one in here, it's 696,000 kilometers, or 6.96 times 10 to the power 8 meters. That's literally what it says, which is roughly about 700,000 kilometers. Remember, when you do the power, you're multiplying by this 10 this many times, and 1 kilometer is 1,000 meters. So if I can write the same thing in here, instead of saying it's 6.6, I can say it's actually 6.96. Instead of saying 10 to the power 8 meters, I can just put 10 to the power 5 kilometers, because a kilometer is 1,000 times, so I have to divide by 3 to convert it to kilometers. It's 696,000 kilometers, roughly about 700,000 kilometers. That's the number, okay? So this is the radius of the sun. Obviously, I need the diameter. The diameter is twice the radius. It's just 2 times this many, 6.96 times 10. It doesn't matter which one I use, but I have to be consistent. If I have it in meters for the sun, I better use the same thing for the moon. They cannot use differently. So that is radius of the sun, and that's all we have right now. Do we have the distance to the sun? Yes, it is. We have the astronomical unit. The astronomical unit is, by definition, the distance to the sun. So the distance to the sun from table 1 still, this is all on table 1. Table 1. We have the distance to the sun, and that is, according to this one, it's 1.495. I'm gonna approximate it to 1.496 times 10 to the power, again, 11 meters. Again, if I do the same reasoning as I did before, this is roughly about 150 million kilometers. Because 1.49, this is the point, by the way, there is a decimal point in here. 1.496 is about 1.5. 10 to the power 11, again, 11 removed from it 3 to convert it to kilometers, so it's 10 to the power 8. And then 10 to the power 8 kilometers. 2 out of the 10 to the power 8, that's 100. So it's 150. And then the rest of 10 to the power 6 is a million. So it's about 150 million. This is a well-known fact. This is something that you need to remember. 1 AU, which is this distance, is about 150 million kilometers. This is something that a lot of people talk about a lot. At the same time, it's 93 million miles. That's the distance to the sun. So if somebody asks you, this is the answer to that, either in miles or kilometers. Okay. So again, we need this number because they're going to go here. The distance to the sun needs to go here, and the diameter of the sun needs to go here. So we have that from table 1. Table 7 also was referred in the problem, and table 7 is actually on the next page. Okay, Appendix A4. Appendix A4 should give you the information of the moon because it has all of the objects in here, and it extends to the next page. Okay, so I have the Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, Haumea, Makemake, Eris, and where is the moon now? Because we need that information too. What am I looking at? Did I miss it? Did anybody? Can anybody help in here? Because it looks like table 7 is not showing me this information right now. Where's the moon's table? Oh, I'm sorry. I missed it. It's on the top of the page. It's on the table 7. Okay, so we're good. Hopefully you guys, maybe it's how we put it on the mark. So table 7, it's on the same page. It's on the top, but you have to be careful with the units now. It's very critical that you need to be careful with the units. For the moon, the radius of the moon, it's given in kilometers. So the radius of the moon, so this is table 7 now. The radius of the moon is equal to 1,738 kilometers. You see how we wrote it earlier for the sun in meters? They gave us in meters. I cannot divide meters by kilometers. Doesn't make sense. I have to divide apples by apples. I cannot compare apples to oranges. I have to compare oranges to oranges and apples to apples. So in this case, since the moon on table 7 is in kilometers, I have to convert the sun's radius to kilometer, or I have to convert the moon's radius to meters, so that the meters cancel the meters or kilometers cancel kilometers. So this is important that you have to, don't miss this step in here. Otherwise, you're going to get some nonsense numbers. Okay. So the moon's radius is going to be, I'm going to stick with the conversion that I did earlier. So this is the number I'm going to use for the sun, which is kilometers. Then in this case, I'm fine with this number for the moon. I mean, for the moon. So the diameter again is going to be twice this much, 1,738 kilometers. Okay. So I'm ready to do that part. Now, the distance to the moon is given to us also in 10 to the power 3 kilometers. Kind of tricky in here. So the distance to the moon, let's put it in moon distance, that is given to us as 384.4, but it's in thousands of kilometers, not in kilometers. If you look at the table on the top, it says 10 to the power 3 kilometers. So I have to restore that kilometers. So again, I need this number in kilometers, not in meters. So I need it actually in kilometers. I can use the 1.49 or 150 million is good enough, okay, for the sun. Here is the question then. If I do the ratios, so moon's distance divided by sun's distance. Okay, so in this case, or the other way around, it doesn't matter. The other way, it's going to be 384.4 times 10 to the power 3 kilometers divided by 150 million. Let me move the cursor down. $150 million kilometers. This is what I was talking about. The kilometer cancels the kilometer. Furthermore, 10 to the power 3 and 10 to the power 6, they cancel, and I'm left with 6 minus 3, which is 10 to the power 3 in the denominator. So the answer should be about 384.4 divided by, we put a calculator in here quickly. I have a nice calculator in this computer. I don't know if I do. Calculator. Not that fancy. So I'm gonna take the ratio of 384.4. I hope that you guys are doing the same thing. So the answer is 2.56. 2.56. Don't forget this 10 to the power 3. When I take it up, the sign changes to 10 to the negative 3. So this is how big the moon is in radius versus how big the sun is in radius. Okay. In other words, the sun is this many times bigger in radius than the moon is. Obviously, you're saying, well, I mean, the distance. I'm not saying the radii. Okay. This is the distance, how far the moon is from the sun. Okay, from the versus the sun is. So in other words, the sun is very far away compared to the moon by this factor. So the moon is very, very close. So if it's about 1,000 times, the moon takes about 2.5, and the sun is about 1,000 times further than that. That's what this ratio means. Okay. Now, the other one in here is the diameter. So again, so this is the distances. Now take the diameters. When I say the diameter, I have to multiply by 2, but that really doesn't matter. So twice the diameter of the moon, which is 2 times 1,738, again, kilometers, divided by the diameter of the sun, which is 2. Again, let me move. Let me find where the mouse is. 2 times 150 million kilometers. Again, the advantage of doing it this way is that this number and that number cancel. And furthermore, I'm going to do a trick in here, and hopefully you guys don't mind it. Wait a minute. 10 to the power 3 and 1,000. So the 2 and the 2 cancel. So it really didn't matter whether or not we use the I'm sorry, what am I saying in here? This is wrong. I hope that you guys caught it. I'm not saying the distance in here. I'm saying the mass, the diameter. This should be the diameter. Can't do the same number in here. We're going to, so this is, again, remember, it was a different answer, so different. So it was 6.96 times 10 to the power 10 to the power 5 or something. Yes, 10 to the power 5 kilometers. So the issue with the kilometer is still the same, but I wrote this wrong number. So the 2 cancel the 2. And again, I'm going to bring this to 3. So I'm going to divide this by 2. So it's 17 divided by this number. So let me do with this quickly here with the calculator and see how much that's going to give me. So I have 17.38. 17.38. I'm hoping that you guys are doing this one on your own also. And if there is a mistake, please let me know. And if it's not clear, also let me know. Again, the answer is 2.497. 2.497, which is, if I round it up, is actually 2.50 times 10 to the power negative 3. The point being in here is they're almost the same number. How big the moon is compared to how big the sun is, and how close the moon is compared to how far the sun is. The ratio is almost the same thing. That's why we have a perfect alignment in here, so that although the sun is much, much bigger, but the moon is close enough so that it covers it completely when you look at it during a solar eclipse. So for you, the sun is completely hidden because this distance over this distance is the same ratio as this distance over this distance. So at the end of the day, that is why you have full solar eclipses and full lunar eclipses, and this is a peculiarity to Earth. This is not true for all satellites, for all different planets. There may be a situation where the moon is too close to cover not just the star, but to cover even the area around the star. And you will not be able to see the corona, because for our case in here during the solar eclipse, part of the corona actually will be visible. And this is because the moon just covers the sun, just about covering it. That's why this is actually interesting for Earth. Or the moon could be far away. In that situation, the moon will cover part of the star, but not completely, provided the other conditions are met too, namely the alignment of the two paths. Because for the case of the Earth, this will only happen rarely. In other planets, for example, in other situations, you might not have a solar eclipse no matter how big the moon is, because it's completely off of the orbit, or it's going completely in opposite directions. Case in point, for example, Uranus. Uranus goes around the sun, and its moons are actually flipping 90 degrees completely. So if you are on the side facing the sun, you're all going to see the sun no matter what. And if it's nice, it's always night. You will not have eclipses, except if the moon actually happens to cross the path of the planets and its path around the star. Then in that situation, you'll have solar eclipses and lunar eclipses. So there's a lot of issues in here at stake, not only the size of the planet, the moon versus the size of the host star, but also how far it is from the star and where is its orbit. So all of this thing creates from interesting variety of problems that you could have out there. Case in point, for example, Mars have 2 tiny moons. Could they even do a solar eclipse? Yes, they could, provided that they are at the right distance, but they are not at this point. Okay, so the point being in here, it's doable provided they're at the right distance and also in the right path too. So that is the point of this exercise. Hopefully that is something to, I know we went through it in detail, and hopefully you guys have an understanding of it. Does this sound clear, or am I being too explaining a lot? Yes? Why is this not showing completely? Oh yeah, because of this. Okay, now I can have more real estate in here, which I really need that. Problem 16, which is actually an interesting problem, and that is the one that is related to that graph. Remember, it says on August 2nd of the year 2027, there will be a full solar eclipse in basically the area of North Africa. The area of North Africa at that point is actually on the prime meridian, meaning at that point in here it's 0 hours with respect to Greenwich. Okay, so they have to keep that in mind. And the problem says the following: a total solar eclipse occurs over Africa on August 2nd, 2027. Okay, based on the 6,585 8-hour, okay, time between repetitions of similar eclipses, when and where will the next similar total eclipse occur? So after this many time that lapses, there will be another solar eclipse. So we want to find it where and when, so that we can make a prediction. We can make when it's going to happen. Okay, here's the trick behind it. How many years? First of all, 8 hours, and that's what I was talking about in here. So if 8 hours this is 0 hours in North Africa, and we go 8 hours later, it's going to put us exactly in North America, right in our time, Pacific Standard Time. So this is Pacific Standard Time. So if it's going to happen, this is -8 with respect to this one. In other words, you will have to wait 8 hours for it to come to this side. So if it's going to happen somewhere, it's going to happen in North America where we are after this many days. Okay. So how many years and days is that? That's the key question. So again, there are 365 days in a year, in 1 year. How many years is 6,585 days? It's easy. 6,585 days divided by 365 days per year. That gives me how many years that is. If I do the math, and I hope that you guys are doing it with me, 6,585 days divided by 365. That gives me 18 and some change. 18.04 something, something, something. Okay, I don't care about the 18. I just want the number of years. So it's saying 18 years after this year, 2027. So I start counting from 2027. 2027, add to it 10 years or 18 years. So 8 plus 7, that's 15. 15 and, 1 plus 2 plus 1, that's 4. So the year is 2045. That's when it's going to happen. But that's not satisfactory. We really need to know exactly what day that is going to be. Okay, that's easy. How many days after 18 years really has lapsed? We want to find 6,585 days. That's all. So 18 years times 365 days, that should give me, according to this calculator, 18 years times 365 days, that is 6,570. 6,570. So it's less than 6,585 days by 15 days. So there is a discrepancy of 15 days in here that I need to account for to bring it to 6,585 days. However, the years between 2027, when it happened in North Africa, and the year when it's going to happen, if it does, in our region of the world, no, not true, David. Okay, you don't have to do that. For the quizzes, no. If David is asking, are we going to do math problems like this one, basically calculations like this one, and the quiz, no. Okay. But other projects, yes. So if you have difficulty with that, please let me know. Does this answer your question, David? Very good. So in the year leading from the year 2027 in North Africa to the year 2045 in North America, we have the year 2028 is a leap year. It's not 365. Remember, I multiplied by 365. So that year is a leap year. So there is an additional day in this one in here that needs to be accounted for in the 15 days. In the year, add 4 years after that, 2032, the same thing is true. In the year 2036, in the year 2040, and in the year 2044. All of these years are leap years, and they have an extra day every year. So I have 1 day, 1, 2, 3, 4, 5 days. I need to count them from the 15 because they are part of the leap year. So in the 18 years, there are 5 leap years from 2027 leading to 2045, and those they have their own extra days anyway. So I really need to find 10 extra days past August 2nd. And if I add 10 days to August 2nd, that should put me on August 12th, 2045 in North America. More specifically, our region of the space and Mexico. So if you happen to be on that time, August 12, 2045, in North America and or Mexico, basically North America, that's Mexico too. But the thing being in here, actually in this region of the world, because also the latitude plays a role too. Remember, North Africa is that part of the world is about 30 degrees, 33 degrees. So that puts us also in here 33 degrees, 34. So we are in an ideal location in here for where the next eclipse is going to, the solar eclipse is going to happen. So let's Google this to see, does this make sense? Can you guys check it to see if it's going to happen? So let me see if I can find something in here. Eclipse, solar eclipse, solar eclipse 2045, because that's our prediction. It's going to be happening next time around 2045. And let me stop sharing. Did you guys research it with me on Google? I'll give you a moment. Let's do it. Find it. Okay, very good. At least David was able to find it. Anybody else was also able to find it? Does it happen on the same day as we predicted, David, or does it happen on another day? Yep, very good. So how about the rest of you guys? Okay, very good. So it's, I mean, you Google it anywhere. This is an immaculate thing. And let me share with you the screen. I just put it actually just like you guys do. Okay, let me share my screen. And this is what it says. I put actually in MSN, I didn't put Microsoft Bing, put solar eclipse of 2445, and it's showing me actually a map of what is going to happen. This is roughly consistent with the 30 degrees path. This is the latitude. So it's showing me the path where it's going to be. If it ever loads. Still loading. Okay, so actually, I wanted this picture. So it's more or less North America and all of that region on August 12th. Wow, we're gonna miss it, at least in here in Southern California. Well, that is when it's going to happen, okay? So probably you're going to go to that part of the world to see it too. Because remember, it's a model that is good for a lot of other things. So hopefully that should help understand this concept. Okay, does this unit make sense to you guys? Including the calculations. Because usually when you do calculations like this, you are far more empowered to understand it better, because then you feel better at it. Okay. Okay, very good. Very good. Are you up for another one, guys? Or should I just tell you how to proceed about this question from 9, unit 9? Okay, very good. Okay, let me show you the one I was going to do also from unit 9. And The one from unit 9 also requires a little bit of thinking to get it right, and that is question 13. Okay, question 13 from unit 9 actually also is an interesting one. It says the first day of the month in the Islamic calendar begins when the crescent moon first is spotted. That is actually the beginning of the lunar month. Doesn't matter which country you have. Okay, usually the earliest this is possible is about 16 hours after the new moon. So the new moon, when the first time is spotted, that's 16 hours later, okay, when you can see it. How many degrees has the moon moved since it was new at this time? Approximately how long after the sun sets will the moon set? If it is just 16 hours past new moon. So if that case, you really have to do the calculation. Remember, we're talking 16 hours in here, but the moon goes around the Earth 29 days and a half. Each day of those is 24 hours. So if I multiply 24 hours to see how many hours the moon will go around the Earth altogether. So every day is 24 hours, and I have 29 and a half days. So if I multiply this two, I'll find about 700 hours, basically, that the moon takes to going once around the Earth. The Earth spins 24 hours, but the moon goes once around the Earth in 700 and some change hours. Well, that is exactly 360 degrees. That is 360 degrees. And as it's spinning 360 degrees, then I can find how many degrees it's going to cover per hour. Because if it goes 360 degrees in 700 and something hours, then I can find how many degrees per hour. It turns out to be about half a degree per hour. Okay. Then 16 hours, because 360 and 700 are the ratio of almost half. Then 16 hours would put it in about 8 degrees. So it has to travel when the sun sets, and when it's seen, when the first crescent is seen, is about 8 degrees, I'm sorry, okay? And based on that, we're going to estimate how long it's going to stay in the sky, because again, it's traveling, it's because of the rotation of the Earth. Remember, the Earth has 360 degrees as it spins, and doing it in 24 hours, and that is, again, 360 divided by 24, that is 15 degrees. So the Earth actually does 15 degrees every hour as it's spinning, okay? So again, that is the ratio with which we will find that's 15 degrees per hour, and we have to cover 8 hours. So in other words, which is 8 hours, slightly more than half of 15 degrees. So in other words, the moon will stay in the sky visible for about half an hour, about 32 minutes if you're careful enough, okay? Okay, I'm going to leave this for you guys to do it in detail. And if you have difficulty with it, or if you want me to do a special session for this one, I'd be more than happy to, because I see a lot of you, some of you actually have left because it's, and some of you are saying it's a little bit too much. But the point being in here is this is week 2. This is the units that we have covered. We still have week 3 that I have to finalize and post it, hopefully by the weekend. Don't forget that you have a quiz also. Don't forget you have other assignments. So as David already asked, and he is rightfully so, are we going to do this kind of calculations in an exam? Or no, you're not, an exam or quiz, but in a homework assignment, yes, you are. Okay, and once you have a homework assignment, and if you're not understanding it or cannot start it because of some reason or the other, please send me a message saying that how to proceed about this problem. Can we have a one-to-one session so that we can understand what to put behind me so that I can put it together and put it and assemble it. If the question is only specific to you, then it's no big deal. We can answer it and hopefully you proceed and you finish it. If we decide, you and I, that this will benefit everybody else, maybe we should record it, then with your permission, I will record it and post it for everybody else to see also. So please do not hesitate to ask. There are resources on the college that take advantage of them if you want to, but do not let it basically sitting on the shelf in there thinking that it's going to resolve itself. It won't. Okay. Well, it went a little longer than probably what we normally do, but that's fine. I think that's exactly the time we're supposed to be ending anyway. So unless you guys have any questions, I'm going to stop the recording and I will see you guys Tuesday. Very good. Thank you.